Well, here I went and did it. I went and made me another modification to Joseph Newman's motor. I better turn off this. There. No echo. I don't want to have to hear myself. If there's an echo in this audio, please excuse the echo. I'm still having difficulties figuring out how this thing works. There may not be. I think I eliminated the echo. I think I had two input sources and they were creating a feedback with each other in my screencast software. Anyway, so this time what I was trying to do was to see if I could add an electrical load, and I had a difficult time of it. So instead of trying to adding an electrical load, I thought, well, why don't I just go with the load that I've got, but tailor it to be a more normal EV motor. And this is what Newman kept pushing for, despite the fact that people thought, you can use this in something else, and it'll be more useful because it's no good in an electric car. And you know why? I'll give you a hint. It's because he was trying to recharge the batteries pack. That's a mistake. And what that does is it creates huge impedances in the wrong places, like in the coil. And that creates heating in the coil, but then you've got the cooling effect of the magnetic field of the rotating bar magnets, so maybe it'll compensate. Anyway, so I went with Greg Tuntland's suggestion. His car, an EV, a conversion, a custom-made conversion, requires 144 volts coming, well, that's what comes from the battery pack going to the motor, and 200 amps. So I thought, okay, I'll try for that. So I had to use a battery pack of 150 volts because by the time it leaves the battery pack and is measured here at in1, if I can find it, where is it? It ends up, well, no, that's what, oh yeah, in1, that's 150. So where was it? Oh, by the time it ends up on the coil, though, it's just under 139 volts RMS. So that's close to 144. So I had to have more coming out of the battery pack than what was going into the than what was showing up on the coil in order to get 140 on the coil. And then he wanted 200 amps on the coil, and here we have 203 amps on the coil. Let's see what else I had to do. Oh yeah, I put in this capacitor here, C2, at 4 microfarads, and I reduced this C1 to 1 microfarad because I didn't need the 10 from before. I kept my 2 neons, it was the only way to do it, and I put a voltage spot here with a name on it, and this is, I don't understand. The out 1 and the out 2 is 140 volts, okay? But the neon reads 80 volts. And what's 80 volts doing in here? And it's 140 on either side on the outside. And then I was trying to figure out, well, are the neons turning on? Are they reaching their breakdown voltage? I couldn't understand what I was reading. If this point here is 80 volts, and this point here and here is 140, and the breakdown voltage is 100, well, the difference between 80 and 140, if you take the average, what is the average? 80 at 220 is 110. So yeah, it should be, but I kept monkeying with the voltages on out 1 and 2, and I couldn't see any difference. The neon bulbs were functioning anyway. So maybe I should have monkeyed with these voltages on the coil, and that would have changed things. I don't know. It looked like they were working because I had a waveform, a complex waveform, a blend between a sine wave and a square wave, just like everything else that's going on in here, except some places we just get a sine wave. So it looked like they were flashing. It's hard to tell, Paul Falstad simulator, it's so much easier. Everything is in real time. Anyway, so let's see. What else? I had to raise the voltage on the spinning bar magnets to 35 volts each. And I had to raise the inductance value representing the electromagnetic field of the spinning bar magnets to 5.5 microhenries. and that's raised up from their prior value, which I believe was 700 pico henries, which is pretty low, especially if we're trying to make a tight coupling here. And then I had to lower the coil. The coil's inductance was 16,000 henries, so I lowered it to 300, and its corresponding resistance to 900 ohms. And that gave me the correct figures that I wanted, which was 140 volts on the coil and 200 amps. What else? So, when you take a look at these figures, how much amperage is taking place on the battery? I don't get to have negative amps anymore, but they're very dinky. They're 300 milliamps on the battery. Now, as I recall, it's something like 30 amps usually, I think, on my car being drained from the batteries. If that's the case, that's a difference of 100, factor of 100, which means my 300 volt battery pack would last 100 times longer. Well, this is 150, so we'll say 50 times longer. So you would get a range improvement of 50 times. Well, 100 times from 60 miles per charge is 6,000 miles. So if I only get 3,000 miles per charge, I wouldn't complain at all. That's pretty good. Assuming I don't have an internet connection at the moment, so I can't check. I should have changed that. I was so lazy. I didn't want to get up. I have my headset already on my head. I don't want to get up and reboot the modem. Okay, whatever. So a range improvement of a factor of 50 to give me 3,000 mile range per charge on a 150 volt battery pack. That's not bad. That's pretty awesome. It's very awesome. Now, this is a 2-coil setup in this motor. I can't call it a proof of concept. How about a proof of demonstration? I don't know. Same thing, I guess. So, is this an electromagnet? Is this a permanent magnet? Usually in a DC, it's a permanent magnet, but this is not DC. Well, this is not DC because normally it's the coils that rotate, don't they? And the magnets stay stationary in a DC motor. But here, the coil is stationary and the magnets spin. So to me this looks like an AC motor offhand, even though the coils here are being fed with a DC square wave. Same thing, 50% duty cycle. And by the way, I was worried that this chopping mechanism representing the commutator was consuming energy because it says 150 volts. So I decided to get their amperage, and it's zero. It's zero. 0 amps on the chopper, on the commutator. So the electrical, equivalent of a commutator, mechanical commutator. So I don't have to worry. The chopper is not costing me any amperage. But we do have to supply it volts in order to work, so I guess it could be taken off the battery pack. It's just not going to drain it any, contribute to its drainage. Well, if these are non-electromagnets, if these are permanent magnets, then I don't have to account for any energy expenditure of the magnets, and so the only energy I have to worry about is the 300 milliamps coming out of the battery pack, which is pretty good, Now what's the wattage? Here's we got a problem. Maybe we got a problem. Let's see. Yes, we do have a problem. No? Yes. We have negative 26 watts on one coil and negative 90 on the other. And first of all, negative watts, what does that mean? Does that mean something I'm supposed to know as opposed to positive watts? But it's not 50 watts. It's not 50 kilowatts, which I believe is what my car, or is that horsepower? See, now that I can't remember. If I had internet access, I could go check. I think it's electrical watts, not horsepower watts. I could be mistaken. Well, let's think about it, though. Let's wait a minute here. 140 volts times 200 amps. Well, let's see, what is that? 140 times, what was it, 200? That's 28,000 amps. How come I'm not getting that figure? That's a very good question. All right, wait a minute. Well, let's go get the program. Oh, it disappeared. All right, let's see. What are we looking at? See, it says watts here, 26.5 watts, negative. How can you get 26 watts? Oh, because the battery pack. Oh, oh, wrong one. Hee. No. No, that's not wrong. 26 it's an 26 watts average. You see, how do they measure the watts on, because this is 54 kilowatt and 45 negative kilowatts. Is that's what they measure when they measure the car? Is, you know, the wattage on the motor is a range, a high and low range of plus minus 50 kilowatts? That could be. Because I'm not getting that in terms of the RMS. So let's see, if we go down here to volts, we already know that, right? We clocked it. It's 139 volts, roughly. And the current is 200 amps. Not the milliamps average, but the 200 RMS amps. So where are they coming from? I guess that, I'll have to assume at the moment that that's what, oh, because they're not doing AC. This is a bit of a deformed AC wave. Although, yeah, this is really an AC motor situation. This is not DC. Sorry, Greg Tuntland. We have left the realm of DC. Well, we know from background information that AC is always more efficient than DC. You can do more with it. You can play with it, manipulate it. So whatever this is over here, this is definitely going to produce an AC field. Either it rotates or it's stationary. One way or another, you know, it's going to have to produce an AC magnetic field surrounding the rotor, so that the DC field surrounding the coil can blend and create this minor modification of an AC sine wave in the coil. Let's see, let's go back down here. Yeah, here it's very, see here we can definitely see the curvature of an AC sine wave component, and then the stepping of a DC square wave. So if we just look at the voltage of the coil. But if we look at the amperage, the current, it looks like a pretty smooth sine wave. So when we blend them, we get almost a perfect sine wave to create the wattage on that coil. Now the rotor is no problem. It's already a pure sine wave. So the rotor has to be an AC field, no matter what, you know, anything else, you know, it has to be for this to work, to give us this advantage. So we still have an advantage, and that is we're draining the battery pack at a vastly reduced amount by a factor of 50 or 100, depending on how you want to do the estimation. Now the henries on the inductance on the coils are quite high. You know, in my car, I think it's 2 henries total or something, and so 300 henries, that's a lot. It's not as bad as 16,000, and that was the table model, but of course that was a little different. You only had one rotor. So there's really 2. This, you know, adds up to a total of 600 henries. But still, 16,000 versus 600, that's still a big difference. So we've brought the weight down. And I had to, in order to get the voltage and amperage on the coil where I wanted it. And I assume the coil is what we're looking at. So this, I'm assuming, is a permanent magnet. something you couldn't measure these things under normal circumstances. Only in the context of the simulator do we get the advantage of measuring the, the current and the voltage on this spinning magnetic field produced by the permanent magnet. So this is the best I can do, and it's still pretty good. It's still pretty good, The battery pack is not recharging itself, but so what, we're getting speed, and we're getting reduction of torque. That was the whole problem. So that we can run this in the car and not try to be strict about this. It's got to be exactly like Newman and recharge the battery pack. No, it doesn't have to. All we have to do is drain the battery pack far less than a normal car would otherwise. And 300 milliamps draining out of the battery pack is pretty good. In fact, it's very good. Let's see. Now, when we run the simulation for a longer period of time, it does become more accurate. Sorry. But we don't gain a whole lot of accuracy. What we gain is a whole lot of time, waiting time, that you have to wait for the simulation to do all the computations before the tracings are plotted out. So I like to do 100 milliseconds because that's a pretty good balance between how long I have to wait, because I have to keep making changes and then wait and look at it, make changes, and run it and wait. It just takes up too much of my time. So this is the right balance in terms of trying to develop this. But if you wanted accuracy, you have to run this at a longer framework if you need precise accuracy. But actually, beyond 100 milliseconds, it doesn't get much more accurate than this. So it's really not necessary. What else? Now, it does make a difference. I don't know what this means. Which way the dots are pointing on these neon bulbs, and I determined that it's best that this one points away out and this one points away out to the outer edge rather than any other direction, and it works. It maximizes output. I could be a little wrong. I may not have tried out all 4 combinations possible of which way these 2 neon bulbs point, but I didn't know it makes a difference. I thought they were exactly the same, but they're not. When you look at the if I wanted to add a plot, a tracing, you look here and you get 4 choices, 2 each on each neon bulb. One's positive volts and the other's negative volts. So it does make a difference. There's actually a top and a bottom to these things, which is strange. I didn't know there was. What else? So when I say electrical load, I mean an EV. I've turned the coils into an EV motor, EV-style motors, so that we can drive with a reasonable speed of 200 amps being supplied to those coils, and a reasonable voltage that's not excessive. It's just the inductance is very high on these coils and resistance in order to get a gainful benefit, which is a drastic reduction of draining the battery pack. But it is slightly unrealistic because I'm assuming a tight coupling between the spinning permanent magnet or electromagnet, whatever it turns out to be, or a stationary electromagnet generating AC magnetic field, and versus the larger coil. Because this is acting like a transformer when you think about it, when you have a motor, except it's not quite a transformer. There are other, modeling a motor coil is a little, or a motor situation is a little more complicated, and there are models, LTSpice models online, but they're a little confusingly complicated, and I didn't want to get into it, so I'm not trying to be that accurate. So this, is really not an accurate simulation of a motor coil as it is. It never was. It's a beginning. It's a baby step. If you want to take it further, then you get to take it further and find out how my simulation is flawed. But I'm a newbie at LTSpice, so I don't try to push it. I don't try to strain myself. I just try to work the concept over, and I don't try too hard at accuracy, although I try a little, but not too much. So don't take this as being accurate, but it's an attempt to be accurate to the best of my greenhorn proficiency. Let's see. What else can I talk about? So I maintain the same high revolutions, which is equivalent to a normal EV. That's probably why when he did his demonstration on his car, he couldn't go very fast because it's not set up to go fast. He would have had to have a mechanical commutator of so many divisions in order to get 100,000 hertz. It would have been very difficult to build that commutator. And here I don't have to worry about that, because his mechanical commutator, when he suggests 20 divisions to the commutator, that means, you know, a hertz of around 50 by comparison to 100,000 here. So I do get better results with 100,000. It's just how would you build a physical commutator to accommodate this simulation? It would not be easy. So if there's an electrical way of doing it, go for it. Don't go with the mechanical. It's just going to be very difficult. But this proof of concept, or whatever we want to call it, does function better at higher frequencies. Newman said that, and it's true. It does. It's much more efficient. And then you can drive at a reasonable speed, you know, instead of snailing along at a snail pace. That's probably why, you know, it was a baby step, and people complain about that baby step, but it was the best he could do for his first or second prototype. That he didn't build too many, as I recall, to fit and run a car, fit inside, you know, under the hood and move a car along. Of course it went at a snail's pace. It went at 5 miles an hour or less, you know. It's not a good selling pitching point, but it's to sell to the public who doesn't know any better. So that would have been better off had he developed it more before he displayed it in public, because it's not impressive. What is impressive is that the car moves at all, and that's what he was happy about, and that's about all you can accept it on that basis without trying to be too critical. Let's see, what else can I discuss? So I'm learning how to do these things. I'm learning how to, it's good to look up impedances. So the only thing heating here is the battery, because now the impedances are totally different than what the prior version I had, version 15, which I had most of my impedance was on the coil, had mega ohms. Now I've got, and the spinning magnet was, I think, nano ohms. Here I've got micro ohms, a little more heating taking place on the spinning magnet, far less heating on the coil. Milliohms, my God, I don't have to worry about that anymore. But the battery, a certain amount of heating, and that's normal for an electric car. All the heat shows up on the battery pack, and then you got to have fans to keep it cool, especially in the summertime. But negative 500 ohms on the battery pack, I don't know what that means. Is that a negative resistance? Does that mean something good? I don't know. But it is 500 ohms, far less than the previous version of several mega ohms on the coil. So at least the battery won't heat up too much. But, you know, batteries are delicate. You don't want them to heat up at all. A coil, you can get away with it. It's not going to destroy the coil. You don't want the magnet to heat up, but of course it never does. It's always very low impedance. Good. We don't want the magnet to heat up. That's definitely one thing we don't want to heat up, because then it becomes useless. But the battery pack, it could boil, it could blow up, you know, if it was overheated. So it does have to be kept cool. And you need fans to do that, you know. My car does that. It has an air intake. And instead of cooling the motor, you cool the battery pack underneath the passenger compartment. The only time you have another fan and a AC is the AC system. You know, a fan on the radiator that cools the radiator that cools the passenger compartment. So that's the only time you need a radiator in an electric car, is to cool the passengers. And I rarely have to run that as it is, because I like the heat, you know. Hey, I sweat a little, you know. Drive around naked or something. Put on clothes before I get out of the car. Or wear a little teeny G-string. Whatever. Let's see. So this is behaving like a normal EV, the way it's set up. The only thing that's abnormal is the very low drainage on the battery pack. But everything else appears to be normal, and so we get an improvement of range. And that's what I always wanted. You know, even if we can't have a self-charging car like Bedini managed to produce in his switching arrangement. Ronald Brandt. Ronald Brandt gave him something to work with because Ronald was blowing up all his capacitors. Or no, was it the transistors? Yeah, I think it was the transistors. They were huge military-style transistors. They looked like hockey pucks. They were so big because they were high voltage, and they're very hard to get. Bedini managed to get a whole bunch. So he had to tweak it, though, so that those transistors don't keep blowing up. But the car self-charged as it drove along. And it did have some batteries. It had four, I believe it had four lead-acid batteries, 12 volts each, but I believe it was four. But it was self-charging, which is pretty good. Here, there's no self-charging taking place, unlike that situation and unlike Joseph Newman's situation, but at least we're not draining the battery a whole lot, so we get improvement over range. Now I'm repeating myself several times over. It just shows how much I love what I've done. Yeah, okay. Don't bore the audience. Let's see. Well, yeah, I put my categorical category names above the category instead of below, you know. That must have confused a few of you. What? Huh? But I still like this side to side, and I have to do this manually each time I redraw the... yeah, whatever. I'll have to make that suggestion one of these days to LTSpice. Maybe they've already made improvements and I haven't downloaded the newer version yet. Let's see. I think that's everything. So I'll post these graphics, and I'll put this graphic, I guess I don't have to put it at the end of the movie, yeah, because you've already been staring at it enough. I guess that's it. And hopefully I recorded the audio this time on my screencast. I think so. I think I've got it right now. No and crickling and crackling anymore, thank goodness. Okay, so turn this off.